Let's take a look at these two counting problems. The first one, a group has to select a moderator and a secretary from 5 members in a group. How many arrangements of group leaders are possible? Then we have a second problem, a group has to select 2 leaders from the 5 members in the group. How many sets of group officers are possible? Pause the video and try to see what is the difference between these two counting problems. Alright, in the first one, we are sure that we have the moderator and the secretary. So, this is telling us that if we would have our moderator and our secretary, let's say student 1 is the moderator and student 2 is the secretary, it will be different if student 2 becomes the moderator and student 1 becomes the secretary. Here, we are to say that order is important. However, in the second problem, we're just asked to select 2 leaders. So, if we're going to have 2 leaders from the 5 members, if I will have student 1 and student 2 as your first leader and your second leader, chances are if student 2 becomes the first leader, it will just be the same thing. Anyway, we're just asked of leaders, not specific positions. So in this specific case, order is not important. And as we can see, knowing whether order is important or not is important because if order is important, then they're counted as 2 arrangements here. Let's change the color so it will be consistent. This one here has 2 arrangements already, while the one here on the right only has 1 arrangement so far. So knowing whether order is important or not is, well, important. Let's take a closer look to a counting problem that would not need order. So you need to choose 2 people on your committee and you have 5 to choose from. You can see that this is without repetition because you can only choose a person once, and well, order doesn't matter. You need 2 committee members, but it doesn't matter who is chosen first. So we're asked how many combinations of committee members would you have? Now, so we have our 5 people here, and based from what we know so far, let's pull that up. From 5 people, we shall only choose 2 committee members. So, based from the counting techniques that what we've known so far, we can use the permutation formula to get this. So therefore, I can have the permutation of 5 taken 2 at a time. And once we calculate this will be 20. So there are 20 possible arrangements of committee members, of 2 committee members out of 5 people. Let's say, for example, we have this member here and this member here. Now, the question is, if we have chosen the third guy first than the first guy, would it matter? The answer is no, because like what was mentioned, order doesn't matter. And here, as you might have seen, I'm going to place back again our third guy as a second choice. There are 2 members that we choose from, and there will be, of course, 2 factorial ways to arrange them. Because if you remember, if we're going to arrange objects or people in a line, there will be n factorial ways of arranging them. So in this case, there are 2 factorial ways of arranging our 2 committee members. This is important because these arrangements are not actually important when we counted the 20 possible arrangements. So because those 2 factorial counts are not important, we have to remove it from the 20. And as we've learned before, when we remove the number of counts from permutation or from factorial, we divide it. So therefore, what we need to do here is to divide our permutation of 5 taken 20 by 2 factorial, which means I would need to divide 20 by 2 factorial. Therefore, what will come out, and I'm going to write it in a formula based here, would be 5 factorial over 5 minus 2 factorial all over 2 factorial again. Mathematically manipulating this so it will become a non-complex fraction, this would have become 5 factorial over 5 minus 2 factorial times 1 over 2 factorial. Then, multiplying this one, I'm going to have 5 factorial over 2 factorial times 5 minus 2 factorial. This will now lead us to having 20 over 2 factorial, and this will actually give us 10. So that meant if we disregard the number of arrangements of the 2 people, because it did say that it did not matter, there are actually only 10 possible ways to arrange, or to get rather, 2 committee members from 5 people. And if we are arranging objects or people where order doesn't matter, we do not call it permutation anymore. We call it combination. So as the subset of R objects from n different objects are called combinations. The order of objects is not considered. It is symbolized most frequently by the combination of n taken R at a time. Sometimes we can also see the sign capital C, then n comma R, or this one here. It's a vertical array, n, then R below, but there's no fraction bar, and close in parentheses. And the combination of n taken R at a time, wherein there are n distinct objects and repetition is not allowed, is given by the formula that we had a while ago. N factorial over n minus factorial times R factorial. Or in other words, we divided the permutation. Let's place it down here. Alright, we'll fix that. We can see that this formula of n factorial over n minus r factorial times r factorial was originally derived from the fact that when we arrange with order our objects, we should remove the number of times those objects taken from can actually be arranged because they are not important. This gives us the formula of combination.